I'm James Hayes. I'm from Carnegie Mellon University, and my advisor is Alexei Efros. And he was actually here almost exactly a year ago today, talking about some of our work that our group does, and I'm going to talk about more. This is all work that I've done with Alosha and also with Tomasz Malishevitz, who's here. So before I talk about IM2GPS, I'm going to take a quick backtrack to some related work of our own, which we presented last year at SIGGRAPH on image completion. So if you have some photograph and you want to, let's say, get rid of part of it because you don't like it, or because that data was missing from however you imaged this, you want to be able to complete this and not have anybody realize that there was data missing, that you manipulated the image. And there's a lot of nice previous work on this. And it can be summarized into two main areas: diffusion-based methods, which are going to kind of propagate colors from the boundaries inwards and maybe try and follow straight lines. They work nice for very thin lines, but for any large hole, you don't preserve texture, so they don't really stand a chance. And then there's texture synthesis methods. And okay, these can preserve texture, but they're explicitly trying to preserve the textures that they see in the rest of the image, but since they have no idea how to reassemble that texture, in general scenes, it's kind of hopeless. So what's so hard about filling this hole? Well, like a lot of computer graphics these days, actually, we're limited in how we can edit an image by how well we can understand the image. And in the limit, you'd have to have like a great deal of image understanding here. You'd have to really parse the image and recognize that this part is a road and that it's a plane tilted at this angle and illuminated thusly, and then re-render something appropriate. And this would all be very, very hard. So our idea was kind of to try and find some other image that had a similar semantic skeleton, some similar scene that was so close, with a building like here and sky and ground, so close that we could just steal whatever content that image had in the corresponding point. And of course, it's a big question whether or not you can find scenes similar enough to permit this operation. And the result of this work that's pretty cool is that a lot of times you can. So here's a result for this image. And the algorithm is pretty simple. For an input image, which would be an incomplete image, you're going to build some relatively compact scene descriptor. This is the GIST descriptor that Antonio Torralba and Aude Oliva developed. It's just basically a measure of how much edge energy there is at different frequencies and different orientations, binned into a very low spatial resolution, say 4 by 4. And then we also have a tiny color image. And then we're going to build those same scene descriptors for a big database of unlabeled images. Well, not big by Google standards, I guess. And then find some nearest neighbors. And ideally, these will be similar scenes. And in this case, they look pretty similar. And then for each of them, we'll try and do some local alignment and then produce 20 image completions and let the user choose among them. So 20 because the scene matching in this project wasn't that reliable. And because image completion is kind of, it's an under-constrained problem. There's a lot of reasonable solutions, and it's kind of up to the user to decide what they want. So in this case, I'm going to overlay it with one of the scene matches at the best alignment that it found. And so here it is before any blending operations. So obviously, you can still see the seam there. And then after a graph cut and Poisson blending, it becomes pretty seamless because the scenes were already so close together. So I guess the takeaway message from this work is that you encounter scenes that are similar enough that they permit photorealistic image editing operations, I guess. And kind of a theme of that research and the IM2GPS that I'm going to talk about is that our belief, at least, is that computer vision and graphics becomes easier if you're in a space of similar scenes. So like this is the space of general images, let's say, hugely diverse. And it's very hard to do computer vision tasks, to detect faces or, well, okay, maybe faces are pretty easy, to parse images when you have to deal with this type of variety. But if you're looking at a certain type of scene, then suddenly you eliminate a lot of variations in viewpoint and scale and illumination and orientation. So it's much easier to build discriminative classifiers or to parse images. So these are just groups of similar scenes. In general, it might be extremely hard to define a plate detector because they're kind of textureless objects that appear very different at different angles. But if you're in the space of similar scenes, then maybe it's not so hard. And the second point is that it's not that difficult to get into a space of similar scenes. For most images, it seems like you are able to find semantically similar neighbors. And that's a lot about what this next work is going to be about. Oh, IM2GPS. All right, so if I show you this image and I ask you where it was taken, which I will do, where was this taken? Yeah, so it's Notre Dame in Paris. And people can say that because it's often viewed and often photographed. So we have a lot of samples of this, and it's visually distinctive for the most part. It's a fairly unique-looking cathedral. So this is a type of landmark recognition. And actually, there's people in Google working on this, as far as I understand. Hartmut Nevin talked about a landmark-based geolocation system at CVPR this year. What about this type of image? If I ask you where this was taken, any guesses? Israel. Okay. Anything else? Still Paris. Okay. Those are reasonable guesses. Not San Francisco? Maybe. I think. I don't think those are very good guesses. I think most people would say that this looks more like Europe than the Americas or Asia. Now, for a computer to recognize this unambiguously, it would be difficult, but maybe feasible. Maybe with sparse visual words based on SIFTs, some very efficient matching, and some geometric verification, and the right data, like Google Street View for the whole world. Maybe this is unambiguous enough that you could efficiently engineer that, give you the address of this. It's a big problem. Maybe somebody's working on it. I don't know. But humans will recognize this in a more generic sense. They can't be expected to have seen that before, and they just kind of have to associate it with similar scenes. Say, OK, it looks kind of like Europe, maybe. Here's another image. Any guesses where this is? Virgin Islands. OK, good guess. Anything else? Costa Rica. Good. There's a lot of other places this could be. I think it's even more generic than the previous one. It could be New Zealand, the Philippines, Thailand, maybe even Hawaii. And for an image like this, I think even if you had Google Boat View for the entire coastline of the world and some efficient matcher, that this scene is too generic and too dynamic to expect there to be any discriminative features that would reliably, match you to the correct location. Not if the tide changes, not if a hurricane hits. So you kind of need to reason about where this might be in a generic sense. Just associate it with similar types of scenes that you've seen before. And in general, geolocating from a single image is impossible, right? There's uninformative images. Sometimes adversarially uninformative because they put up an Eiffel Tower in Las Vegas, say, things like this. They're trying to trick you. So first, we need a lot of data. So for this project, we got 6 million plus, maybe 6.5 million geotagged images off of Flickr. This is images annotated by the users themselves. They seem to be pretty accurate. I'd say that they're 99% accurate within a few kilometers. I'll scroll over to the next hemisphere. So the map is it's a jet color map on top of a world map. So you can see that there's peaks and population centers and tourist destinations, not surprisingly. And if we look at a random sample of these photos, this is the type of stuff you see. So it's very diverse. Some of it is specifically recognizable as a landmark, like Sagrada Familia. But most of it, you could kind of only reason about in a generic sense. And most of it would be very challenging, in fact, to try and say where these pictures were taken. So for any given query, we're going to look for similar images in this data set, and we need to decide what features we're going to use to compare images. So we're going to start with several of them. So inspired by Antonio Torralba's work, we're going to try tiny images, just the simplest thing you can do, right, is make a low-resolution image and compare images pixel-wise. So just 16 by 16 in this case. Another one is color histograms, and something used in image retrieval literature a lot. Text on histograms, so this is a filter bank-based text on histogram. with 512 entries. So line features, and what I mean by that is we find straight lines in images, say start with canny edge detection, look for straight line segments, and then make some histograms of the statistics of those segments, like which direction they were pointing and how long they were. Another feature, geometric context. So this is the work of Derek Hoym. And in that, given a single image, it's going to assign a probability for any segment to be ground sky or vertical, and also some other subclasses. And then finally, just the same gist and color, small color image that we used in the SIGGRAPH paper that I just showed you. And if we find nearest neighbors using those features in this data set, this is the type of result you get. So that's the image I showed you before. And here are a lot of alleyways that are, as you can see, very structurally similar, similar colors, semantically similar, about the same scale, and actually geographically similar to some degree. If you look at the text labels under all of those, you can see that they're pretty much all in Europe. If I plot those on a map, this is the first 500 nearest neighbors plotted on a map, actually. And OK, so there's peaks in the population centers like Rome and Paris and London. But if you look at the rest of the world, there's almost no confusion. An image like this only seems to come from Europe. So it is geographically informative to some degree. If we want to make explicit guesses, instead of just having this probability map, then we can look for modes in that distribution, say with just mean shift on the geographical coordinates of all these matches. And the peaks come out in places like Barcelona and London. This image was taken, in fact, in Barcelona. And that's not where our biggest cluster of matches is. They're kind of in Germany. So it wouldn't be our first guess in this case. So this might be a failure case. But it's still reasonable in the things that it's getting confused by. Now, if we go back to the landmark image, lots of people photograph these. So for a lot of landmarks, even though our feature set is mostly global scene statistics and not especially discriminative, you can still find landmarks pretty reliably. And then, yeah, the biggest cluster is going to be in Paris. And then if we look at this image again, there's more confusion. There's scene matches all over the place: Philippines, Maldives, Palau, Mexico, Thailand, Arkansas. That one's maybe not so good. Most of them look pretty reasonable. The biggest cluster happens to be in Thailand, which is the correct one, but it's not bigger by much of a margin. So we got a little lucky there. But again, the confusions are pretty reasonable if you look at where the other clusters are, warm tropical coastlines. And here's another image. So all the scene matches are in the American Southwest for the most part. I mean, there's some other reasonable looking scenes elsewhere, but definitely hones in on the American Southwest, which is correct in this case, even though what's interesting, I guess, is that none of the scene matches are the same physical scene. They're all just geographically nearby scenes that are correlated in some way. Color and texture are pretty discriminative in this case. It doesn't need to be outdoor images. Here's basketball court, and it tends to peak cities that have NBA teams, things like that. Picture of a zebra in Africa. So the scene matches are, again, not discriminative to the level of zebra recognition, but just recognizing this type of grass texture with foreground objects does tend to get you a lot of matches in Africa. And the biggest cluster is in Kenya, which is the correct location in this case. All right, so let's quantify the actual results. So the test set it's 230 images. I showed you a quarter of it before. And this is performance of our algorithm with respect to database size. So over here is the full database, 6.3 million images. The likelihood that the first nearest neighbor scene match is within 200 kilometers of the query is about 16%. So in absolute terms, it's not terribly impressive, but you saw the data set, right? It's pretty challenging. As you decimate the data set down to nothing, then performance goes to chance. Chance works out to be 1% in our case. If you take two random geotagged Flickr images, there's a 1% chance that they'll be within 200 kilometers of each other. So yeah, my feeling was that this task was pretty hard, and I wanted to actually see how well humans do it, just, I don't know, out of my own curiosity. So we've started to run some little pilot user studies asking humans to do this task. You give them an image and you say, where was it taken? They answer that by rotating this globe around and putting the crosshair on their guess. And to help the humans out, I gave them a political map that has mountain ranges on it and has all the population centers on it. The humans might need more help still. They can say, oh, that's the Forbidden Palace in Beijing, and then kind of, where is Beijing? I don't know. But then again, if they don't know that, then maybe they really are failing the task. They've only associated this image with a text label and not a location. I don't really know what would be fair. But it seems to me that humans are probably doing around 10% on this test set. There's going to be a huge variance here, though. I mean, if you give it to a child, then they're just not going to have the experience with the world to know where things are. If you give it to an expert and give them enough time, then they're going to do really well. I don't know what the limit is, but maybe even 50% or something on this test set. If you're forensically accurate and you can leverage knowledge about geology and vegetation and culture really well. Most humans can't do that, so they don't do that well. If we look at the performance of individual features, we can see which ones do well. So the green lines are the percentage of times that the first nearest neighbor matched only with that feature is within 200 kilometers. So with all features, it's 16%, just like on the previous plot. You can see individually, the GIST descriptor does pretty well. But some other features do well, the texture and the color, especially after clustering it, and even these line segment statistics. And these ones benefit from the clustering, I think, because they're just weaker features, so they kind of need more matches to reinforce each other. So the tiny images in the geometric context weren't very useful. So for all the results I've shown so far, actually, it's just these 4 features that we've used. It didn't really help or hurt to include the other 2. Here's just real quick another quantitative result where we can say, well, how does performance change if we allow the algorithm to make multiple guesses? And here we can see that the clustering really helps. This is the purple line. That after, say, 6 guesses, then the median error among the best of those guesses is within 500 kilometers. So if you give it a lot of guesses, then one of them is bound to be right. And again, we're doing a lot better than chance. So, all right, here's another result. And this is pretty common. The scene matches look pretty reasonable to us, as in semantically they look kind of similar. This arid highlands. But geographically, they're not well clustered. In fact, none of them correspond to the correct location, which was Morocco in this case. We have clusters all over the world in reasonable places, but they're just incorrect. But because they are well correlated with some geographic properties of the world, the location of those, we can still use this geographic estimate to get some more knowledge about our query image. So let's say we have some secondary source of geographically arranged data, which is just a map, right? That's all a map is, right? Some geographic data arranged on the world. So this is a map from NASA, which I've taken the derivative of, so I get global gradient elevation. It's just how hilly it is everywhere in the world. And you can see Indonesia and the Himalayas and Chile, things like that. So if we sample that map at every location that we thought this image might be located at, we just sample all those locations on average, let's say, something very simple. Then we arrive at an explicit elevation estimate or hilliness estimate for this image, right? And let's say I'll do that for the whole test set. And what I'm going to show here is the top and bottom results of the test set. They're being sorted by their estimated hilliness. And their hilliness was estimated through their geolocation, or through their estimated geolocation. So it's very reasonable. The ones up top are extremely mountainous, including this one that we couldn't accurately geolocate, but we could at least tell that it was a mountain. And then on the bottom are a lot of cities, actually, because cities like London and Paris are in very flat regions. We can do the same thing for any geographical data. This is population density. And then we sort our test set by population density, the estimated population density. And the first one is Hong Kong, and then India, and then London. And then in the bottom, we have these barren regions. And again, we didn't use the actual known geolocation of these images. For each image, we estimated where it might be in the world and used that to index into some map. Here's another map. This is land cover classification from NASA. So for each of these classes, we can say, well, which members of the test set are most likely to belong to this class. So snow and ice, you see these glacier images on the top. We kind of run out of snow and ice images. Again, the test set's about 240 images. This is sorted by probability of being forest. And the first two here are mountainous, but they are forested. And there was no mountain class in that land cover classification map, so that's the correct class to put those in. Savanna, probably only a few images in the test set really correspond to savanna, strictly speaking, but these are some of them that are kind of more evocative of savannas. Water. I've just showed you sorting so far. We can have a classification task. I think I'll just go through this quickly. We can get a ground truth light pollution measure, say. So this was a map of light pollution, again from NASA. So for each member of our test set, we can assign it its ground truth light pollution, and then sort that set, and this is the first half. And this is the second half. The yellow ones, we've split down the median, and so these yellow ones we're saying are urban, and the other ones we're saying are rural. So this is like ground truth. And then we can use our geolocation estimates instead of the ground truth geolocation to estimate the amount of light pollution. And this is the resulting ROC curve. It's a binary classification task, urban versus rural, so chance is 50%. But in the best case, this best one has area under the curve of 0.84, I believe. So it's not bad. Here's the actual, this is our estimated light pollution now. It's sorted by estimated light pollution. And the red ones are mistakes. So I think these results actually look very reasonable. So if you look at the first couple of mistakes, those definitely look like rural locations. But according to their actual GPS coordinate, it was in a city. I mean, you can't tell. Oh, that first park is in London, so oh well. I think a human would probably rank them very much like this as well. And here are the things that it thought were cities. And again, I mean, that definitely looks like a city to me, but for whatever reason, it didn't have enough light pollution at its actual location. All right, so I'm going to talk about some failure cases now, and at the same time, I'm going to use that to motivate geolocation driven from local distance function learning. And so what I'm about to talk about is inspired by the work of Andrea Frome of Google, who's sitting here, and in collaboration with Tomasz of Google, but also of CMU, who's sitting here. So this is one of the results. This was a member of our test set. And we estimated this to be its most similar scenes. Okay, so 3 of them are pretty reasonable, but a lot of them are garbage. And you've got to ask, well, how many, we've got to have more pictures of the Sydney Opera House in this data set. It's hard to know, but we can check. Here's the map showing the distribution. So it peaks in between London and Paris, which basically means it was chance. But if we look only at the scenes, only at the images that were actually from this geographic area, and then try and find the most visually similar images, this is the set we get. So we did have a lot more Sydney Opera Houses in our data set. The scene matching was just not doing a very good job. And this is showing the distribution of these. So you could say that these are now, let's consider these goal images. This is what we wanted our scene matching to produce when we searched the whole database. And we'd like to coerce the scene matching to produce these results somehow. And so we're going to try and learn a new distance function. And the distance function we're learning is of a pretty simple form. It's just going to be a weighting on the elementary distances, a strictly positive weighting. So before I mentioned 6 elementary distance functions, now I'm going to have 20 because I've added some more sub-features. And we're going to have an optimization that weights each of these different distances. So like the distances between the 5x5 color images, or the distance between the color histograms. So the absolute numbers don't matter. They're only the relative sizes do. This is showing the relative weighting of various features that we have. And they're still mostly kind of global scene property features. And this is what the optimization learned for this Australia example. And then this is the new scene matches using those distance weightings applied to the whole data set. So this is not a geolocation result because I've cheated and I used, you can see it peaks in Australia now, obviously. I've used the actual location of this image to help train the distance function. So really what this is an example of what the training result looks like from this local distance function learning. So what we could do is apply this little algorithm to every single image in our data set. For every image in the data set, we can say, okay, what are your nearby visually similar images? All right, I want you to return those scenes, and I don't want you to look like any of the other images from hundreds of miles away. And we can run this rather large optimization on all 6 million images, but that's a bit computationally prohibitive, so we need to find some more clever way to do that. But I'm going to show you some more of these local distance function learning results, kind of in the hope that that when you've learned one of these for every exemplar in your data set, that you're going to get similar results for a novel query, which I think is fair. You could say, oh, you're just overfitting here because this is training data, but the distance functions we're learning don't really lend themselves to overfitting too much. I mean, it's just a positive combination of other feature weights, and those features are pretty global scene properties. So here's, this is the Barcelona query I showed you earlier. And this is, this is the results that we saw earlier. And now if we find limit ourselves to our kind of geographic neighborhood and then find the most visually similar scenes, well, I mean, that looks pretty similar to me, actually, like a similar set of alleyways. And if we try to learn a distance function which keeps these closer to us than the rest of the images, it doesn't really work. We get almost the same results that we got before. So it wasn't able to improve this one. If the geographically nearby images just aren't more similar along any axes, then there's nothing you can do. And that's good. I mean, it shouldn't overfit the data and try and force it. Okay, so again, here's another image. Here's its nearest neighbors according to just the default weightings of the elementary distances. And okay, partly by luck, it's peaking in Italy, which is the correct location, although it's not actually matching to any of the same physical locations. It's just finding other similar monuments in Italy, which is reasonable, I guess. But in this case, if we look at the geographically nearby matches, we can see, oh, there were actually a lot of other pictures in the data set of this exact physical artifact. Not just these towers, but all of these images actually are El Duomo in Florence. They're all just a connected group of buildings, and they all have similar patterns, this very strong linear textures on them. So if we learn some distance function for this example, and then apply it to the database as a whole, then now we are able to find much better nearest neighbors. And here's another example. Default distances. It's kind of peaking in London, which is not very reasonable for that query. Here's the geographically nearby and visually similar images. And okay, those look a lot better. To a human, those seem like they should have been the matches. So when you try and force them to be similar, it finds some weighting. Color happens to be very, very discriminative in this case, I guess the golden and brown tones. And now applying this again to the whole data set, here's our nearest neighbor. So now it's finding a lot of exact matches. And just a similar thing. This is Sacré-Cœur in Paris. The initial matches are terrible. But if we try and force it to be like the geographically similar images, then this is the result of the learned distance function. So everything I've shown so far is it's kind of landmark based. I'm just showing you, okay, now it does better on landmarks. We're kind of training it to go from category level recognition to instance level recognition maybe, which is nice. But why I'm really interested in this work is to try and is the hope that by forcing things, by using this local distance function learning, that will improve scene matching in general. So I'm going to show more results that maybe support that. So here's a query, and here's its default set of nearest neighbors. And they're not bad. I mean, it's nighttime, and they're mostly urban, but not all of them are skyline pictures. There's a fair amount of these concert pictures, and just not appropriate scenes. So here's the geographically nearby and visually similar images. So this is Hong Kong, and once we've limited it to Hong Kong only, now the scene matches look a lot better. And after the local distance function learning. All right, so what we would have liked to see is we would have liked to see Hong Kong. We have 3 matches now be the dominant match, but it couldn't quite manage that. Although now there's more Hong Kong matches. The nice thing is, though, the confusions look more reasonable now. It's got all of these other nighttime skyline pictures that weren't there before. So this is kind of encouraging. And here's the picture of Thailand again. And these are the matches I already showed you in the order that I already showed you. And if we limit ourselves only to Thailand photos, here's the scene matches. And then this is the weights that the local distance function learning chose. And here's the new neighbors for this query. So we got more pictures of Thailand, and which is great. And we've kind of filtered out some of the unreasonable ones. I'm going to skip ahead a little. All right, so another query. And these are the default nearest neighbors. And they look good at first glance, but if you look closer, you realize that a lot of them are not snow. This is sand, sand, sand. Mexico, that's sand. And Athens, that's just stone. So a lot of those are actually not snow. They're actually pretty bad scene matches if you examine them more closely. So if we coerce it to instead match to more geographically similar images, and these are similar images from Canada, then not only do we now do better at geolocation, we have some images of Canada, but we've gotten rid of all of these images of snow. So it's actually matching, we've gotten rid of the images of sand, sorry. So now it's actually doing a better job matching in a generic sense, not just in a specific geographic sense. Another result. These are the default nearest neighbors for this query on the left. Here's the geographically near similar images. And here's the result after local distance function learning. So you'll notice that initially, a lot of the confusions, a lot of the not very good matches were kind of, tropical islands seen from the air, things like that. But if we limit it, only to pictures of England, then it kind of learns that, oh, this shouldn't be, so much of a tropical island. This is probably more like things in the air. So we get a lot more sky pictures. This is my favorite result. So the nearest neighbors for this query using the default elementary distances, the default weighting, which is just all of them equal, are really terrible. This first scene match is maybe reasonable because it's at least outdoor in a similar climate, but most of the others are just really bad. They're texture images. They're semantically unrelated. So if we limit it to similar images from Afghanistan and India and Pakistan, then these are the nearest neighbors, which is markedly better. Now they are actually outdoor images in the same climate of the right scale. So in general, this local distance function learning has helped quite a bit. If your nearby images, if you don't have nearby images that actually look like your query, so in this case, this is the query in all cases actually, and it was from Libya here, and it couldn't find enough similar images in Libya, so it kind of expanded the radius to include Greece, and then even among those images, it just can't find anything similar. It's a very odd image. It's very overexposed, and it's pretty uniquely composed. So it can't find anything similar. So of course, you can't learn a meaningful distance function. You can't improve your geolocation or your scene matching. And here's another failure case. So this is from Maryland, and apparently there's some kind of tank museum in Maryland, and it decided that this house would be similar to a lot of tanks. All right, so in summary, I think that using this geographic labels that we have and forcing images to be similar to their geographic neighbors is actually improving the scene matching in general, which could improve a lot of other computer vision and computer graphic tasks that leverage scene matching. But what I've kind of showed you isn't real results. It's kind of initial training results, and I hope that that's indicative that if we were to do this on our entire 6 million image database or bigger, that we would get qualitatively similar results. All right, if you guys have any questions, please let me know. Yeah?
When you retrain the weights for your distance function on local matches,
Mm-hmm.
the weights, are they at all consistent across different variants?
Well, I mean, not really. I mean, for each query image, it's picking out certain features that happen to be discriminative for that scene.
Can you repeat the question?
Oh, yeah, of course. So he's asking if there was any consistency in the distance functions learned for different scenes. And I was saying that, not really. Different scenes pick out different features or different combinations of features, which happen to be discriminative in the case of that scene or that class of scene. It's never one feature by itself. That would never really be discriminative. It's always some combination, but sometimes one is weighted much more than another. Did I answer that well? Okay. Mm-hmm.
Well, just following up on that, what if they were two geographically and visually similar scenes? Then are the weights similar?
Okay, I see what you're saying.
All right, so just repeating, what if they're visually similar and geographically similar? You'd like the weights to be somewhat similar, but do you know if they were?
Right. I guess I haven't explored it well enough to answer that. My intuition is that, yeah, they would be. I mean, that needs to be the case for this whole thing to work. Because in this local distance function learning, what you're giving is you're giving every example point in your data set a decision process that it gets to execute anytime you have a query. So the exemplar gets to decide whether a new query is its neighbor or not. And it has to be the case that that two similar scenes would produce the same type of distance function, or else the framework just won't work because the thing that the exemplar learned won't actually be appropriate for the query. It's difficult to explain. Yeah?
So have you tried an unsupervised approach, tried to group the images and then assign the labels for location? Did you try any unsupervised thing?
Well, I mean, you mean, I don't quite understand your question.
Grouping the images so that you'll have a lot more samples. But
You mean grouping them visually or geographically? Okay.
based on this descriptor or
Mhm.
any other descriptor. And then after the grouping, you can also try assigning the labels to the groups, which may has a little bit visual variety.
No, I haven't tried that. No. We didn't, the only clustering we did there was kind of an after the fact, after we had our scene matches. We tried to cluster them geographically in the hope that it would kind of throw out outliers that, the largest mode of the mean shift would be the correct geographic location. And, it does help performance a little bit, but not that much actually. Yeah?
So one of the things that I thought, first is just a comment. One of the things I thought was really interesting was you're sort of implicitly leveraging like a prior on what are popular
Yes.
things to take pictures of, right?
Yes.
So, there are a lot of glaciers in the world, but maybe there's only a few that people actually like to take pictures of. So that part's
Exactly.
pretty cool. And so as far as the question is, so as far as the local distance function, I don't know if I missed, but how would you use that, like in some application?
Well, I mean, so ideally, if we've learned better distance functions for every exemplar in our database, all 6 million of them, then when we try to do geolocation estimation, then then the results are going to qualitatively look like the much better results that I kept showing after the local distance function learning. So I mean, I don't know. I think it could almost double the performance of this geolocation task. But beyond the geolocation task, it appears that the scene matches that come out after you've learned a distance function are more reasonable, not just geographically, but according to all other relevant semantic properties, like, I don't know, climate, which objects they're likely to contain, what the scale is. So, I'm hoping that the scene matches will be better for whatever other computer vision or computer graphics tasks leverage scene matching, which right now might not be that many, but I think there's going to be more and more being published in the near future.
But I mean, if you're given a new image, it's
Yeah.
not in your database.
Right. Well, yeah, so each exemplar, so let's say this is an exemplar in our data set, which it is. After the local distance function learning is done, the exemplar has a decision process to decide which things are its neighbors or not based on the weights that it just learned. So when you get a new query, every single exemplar is going to, execute its decision process. So this one's going to decide, was this new query a neighbor to me or not? And it might say no, it might say yes. So, I mean, that's how it works. It's kind of weird because you're twisting things in reverse. You're letting the individual exemplars decide the neighbors with a different distance function for each of them. Mm-hmm.
So when you went to local distance learning, you're implicitly trying to force out features from the given image, right? The most prominent ones.
Mm-hmm.
Have you tried the other way where you let those features come out of your feature vectors? So instead of assuming you have a fixed way of computing distances,
Mm-hmm.
if you come up with some nonlinear squish-squash way of computing distances which was learned to be locally smooth.
Tomasz might be able to answer this better, or Andrea. I haven't played with any of these other ways of learning nearby, learning your scene matches better. But there are a lot of really clever ways that I think you could do it, and this is just one of them. And this, it's pretty limited. We're only learning scalar weights for the existing distance functions. So what you suggest might be nice. Mm-hmm.
Is time of day or date of the year of information available on these photos? And could you use something like, if it's an outdoor scene, it's likely to be during the day, or in the evening, it's likely to be inside, to do some sort of correlation?
To answer the first part, technically, yes, every one of these images has a time of day and a date attached to it, but they're generally very inaccurate. The timestamps come from a camera, and the camera is being used by a tourist from New York in Paris, so the time zone is incorrect or ambiguous, or they never set the date on their camera to begin with. People usually don't correct this after they've uploaded it. That's just the EXIF data from the photo. So you can't trust the absolute time and date very well. Maybe you could trust what month it is better, but maybe not, because if the camera doesn't have EXIF information, then instead Flickr just fakes it, just gives it instead the time when it was uploaded, which is kind of unfortunate. But yeah, I wish that data were more trustworthy so that we could explore these other things like you mentioned. I mean, instead of just estimating geolocation, you should be estimating time as well. It's another axis. And I'm sure there are a lot of correlations there. Yeah.
So on a similar line, I guess one of the interesting things about the problem you're solving is that the input is just a single image.
Mm-hmm.
But one can think of other domains where we might have more meta information with that image. For instance, if the image is on a web page, then we'd have context around it. Of course, EXIF information is not always reliable. So I was wondering if you've explored other input parameters that could help to find similar images, either on the geographic axis or for whatever the computer vision or graphics application might be.
No, I can't say I have. But the only label source, the only data source I've actually leveraged is the GPS coordinates. Although, yeah, there's a lot a lot of other cool ways to try and do it. Anything else? All right. Well, oh, yeah.
Have you ever tried saying, I mean, I know your stuff is basically done with a single image. Have you ever tried taking a short series of images and saying, okay, you know, this one clusters in Beijing and Hong Kong and New York, and then this one clusters in Hong Kong and England. Well, Hong Kong is common in this
exactly.
series of England.
Yeah, that's something we're looking at right now. So I said that you can't trust the absolute timestamps at all, but maybe you can trust the derivative of timestamps. I mean, if the pictures were taken 5 hours apart, then maybe you can trust that difference actually. And if you have a set of images and you know that they were taken within a certain amount of time and you know what each of them cluster individually, then it's reasonable to say, okay, could they have actually traveled this far in this time? If not, okay, they must have only been in Hong Kong. So yeah, it makes sense. You could definitely do a lot better if you're leveraging sets of photos. And I'd imagine with somebody's random pictures from Paris for a day out, any individual one of them might be quite undiscriminative, but there's bound to be a few in there that are really discriminative. And I think with a set of images, you'd do really well on this task. Anything else? Yeah?
In that case, let's thank James. He's given us one more demonstration of what large data can do. So thank you for coming over and giving such a nice talk.
Thank you.